Welcome to Chapter 17, Inferences about a Population Mean. We're going to review the first four-step process for confidence intervals and tests of significance. Then in this chapter, we're going to look over the conditions for inference about a mean. We're going to look at the t-distributions, the one-sample t-confidence interval, the one-sample t-test, using technology for matched pairs t-procedures, and the robustness of t-procedures. We're going to look at first the four-step process for confidence intervals. The first thing you should do is state in the practical question that requires estimating a parameter. Plan. You need to identify the parameter, choose a level of confidence, and select the type of confidence interval that fits your situation. Solve. Carry out the work in two phases. Check the conditions for the interval you plan to use, and calculate the confidence interval. Conclude. Return to the practical question to describe your results in this setting. The four-step process for tests of significance. Number 1, state. What is the practical question that requires a statistical test? 2, plan. Identify the parameter. State the null and alternative hypotheses, and choose the type of test that fits your situation. 3, solve. Carry out the test in 3 phases. Check the conditions for the test that you plan to use. Calculate the test statistic. Find the p-value. Number 4, conclude. Return to that practical question and describe your results in that setting. Now, in the last chapter, these conditions for inference about the mean will look very similar except for the last one. The data are from a simple random sample of size n. The population has a normal distribution with mean, mu, and standard deviation sigma. Both mu and sigma are usually unknown. That's the one that's different from Chapter 14. In Chapter 14, we knew what sigma was. Here we don't. So we're going to use inference to estimate mu. But the problem we have here, since sigma is unknown, we can't use the z procedure that we previously learned. What's going to happen in this chapter is we're going to use the sample standard deviation, which is its symbol is S, to estimate our population standard deviation. Its symbol is sigma. When the standard deviation of the statistic is estimated from the data, the result is called the standard error of the statistic. So the standard error of our sample mean now will be S divided by the square root of n. So let's look at what our t-statistic would be, our one-sample t-statistic. When we knew what sigma was, our z-statistic was x bar minus mu naught over sigma divided by the square root of n. Remember where sigma was the population standard deviation. When we don't know that, that's when we have the t-statistic, and that's x bar minus mu naught divided by s divided by the square root of n, where s is our sample standard deviation. So we're estimating sigma with s. We're estimating the population standard deviation with the sample standard deviation. By changing that denominator to be the standard error, our statistic is no longer following a normal distribution. It follows the t-test statistic follows the t-distribution with n minus 1 degrees of freedom, where n is our sample size. So now when we have to find our test statistic, we're going to have to know both our confidence level and our sample size so that we have degrees of freedom. So it's time to look at these t-distributions, since we're going to have to use them to find our our critical values, that is. The t-density curve is similar in shape to the standard normal curve. They both are symmetric, about 0, and are bell-shaped. The spread of the t-distributions is a bit greater than that of the standard normal curve. So that means that the t-curve is slightly fatter at the tail ends. There's more probability at the tail ends than at the standard normal distribution. As the degrees of freedom increase, the t-density curve actually approaches the standard normal curve. In other words, the t-distribution will look very, very, very similar to the normal distribution as our sample size gets large. This is because our sample standard deviation gets closer to the true value of the population standard deviation as our sample size gets greater. The law of large numbers, if you remember. So let's take a look at the t-distributions. The dotted line is a t-distribution with 2 degrees of freedom. As you can see, the tail ends are a little bit thicker. There's more probability underneath that tail end. As our sample size increases, watch how that distribution starts to get closer and closer to the normal distribution. It starts to hug it. And as our sample size gets larger and larger, it really approaches the standard normal distribution. So now it's time to start using and trying to find critical values with our t-distribution. So what I'm going to do is I'm going to pull up the t-chart, and you're going to find the critical values for a 90% confidence interval with these particular degrees of freedom. But let's look at an example first. It's table C is our t-distribution critical value. Now along the top you see different confidence levels. Now the reason why we have to do it like this, where we can only find a critical value for a certain number of degrees of freedom with a certain confidence levels, because we have each of those degrees of freedom is a different t-distribution. So if I wanted to do a 80% confidence level, and I had, let's say, 14 in my sample, what would happen is I'd have to first find out the degrees of freedom, and the degrees of freedom would be n minus 1 or 13, and then I look at the column for the 80% confidence level, go down to 13, and where those two intersect, 1.350 is my critical value. And it's the way that you'll see me write it is T alpha over 2 comma degrees of freedom. The comma in between those two just means that we need to know both the confidence level and the degrees of freedom in order to know how to calculate our critical value. So let's look at another example. If I told you the degrees of freedom, now not the sample size, but I actually say the degrees of freedom are 10, and I wanted to do a 90% confidence interval, what is my critical value? And we'll go to the chart. I want you guys to look at the chart and see what that would be. Well, if we're looking for a 90% confidence interval and 10 degrees of freedom, it would be 1.812. Now, I want you guys to take a look at this next slide, stop the tape, make sure you can do it, and find the critical values for these problems right here. So I would like for you to stop the tape and please find the critical values for these different confidence levels with these degrees of freedom. Now these should have been the values that you got when you looked up on your chart. And what you see here is I wrote it up properly. I said the T alpha over 2 degrees of freedom for the first one. Remember, for a 90% confidence interval, alpha is 1 minus that confidence level. So alpha is 0.1. So alpha over 2, 0.1 divided by 2 gives you that 0.05. So T 0.05, comma 6 means I have a 90% confidence level with 6 degrees of freedom. I look on my chart for the 90% confidence interval, and I go down to degrees of freedom to get that 1.9473. So please take a look at these answers and make sure that you too can replicate what I did. Don't worry about the subscripts to the T, the critical value. That's not as important as you just getting the answers. Well, that's all for now. See you next time.